today we are going to look at heat transfer with opposing, assisting flow, or opposing flow. So we have natural convection that makes this want to go up, but we have flow that's forced convection trying to help it up or make it go down. And so we're going to determine the Newson numbers for each of these. So let's do that. We have this table of information at the film temperature, and we know that this is air. Air is not water. That means it's an ideal gas, which means it follows the ideal gas law, which means that the beta is just 1 over the film temperature, which is 1 over the average, so 20 plus 40. So 20 plus 40 divided by 2 plus 273 to get into Kelvin. This needs to be in Kelvin. This number, when we type into our calculator, is 0.0033 Kelvin to the negative 1. Perfect. So now we have to compare the Grashof number to the Reynolds number. You may ask, why do we have to do that? This is always going to be the first step if you have both forced and natural convection. So the Grashof number is for natural convection, and the Grashof is for natural convection, and Reynolds is for forced. So we need to compare them to see which one is dominating, or if it doesn't really matter, then you have to do both. So if we have the Grashof number, and then we have Reynolds number squared, this is how we compare them. So being less than 0.1, that means Reynolds number is really, really big, and Grashof number is small comparatively. That means forced convection matters, so forced. That's what we really care about, and we can just treat it like it's a normally forced question. Or we have Grashof number and Reynolds number is greater than 10, or it's about 10. Then it is natural convection. The number that's associated with the natural convection, Grashof number, it's really high compared to Reynolds number. So that means that natural convection is dominating, and so we can just treat it like a natural convection problem. To figure out which one we do, though, we have to actually calculate these values. So we go back to what we've been doing for a while and calculate Reynolds number. Reynolds number, velocity times the characteristic length over the kinematic viscosity. All right, what do we have? Well, there's a characteristic length. That's an easy one. We're given the kinematic viscosity and 0.4 meters per second. 0.4 times 0.2 divided by 1.608 times 10 to the negative fifth. I forgot the 10 to the negative fifth and writing this. All right, so let's type that into our calculator. We get 4,975. And what we were doing in past videos for this chapter, the Grashof number. So the Grashof number is G times beta times the temperature difference times the characteristic length cubed divided by the kinematic viscosity squared. So this is metric 9.81. Beta we just calculated earlier. The temperature difference, 40 minus 20. The length we said was 0.2 cubed. And the kinematic viscosity squared, we just established that I forgot the 10 to the 5th for that, 10 to the negative 5th. Be sure to square this entire thing, not just the 10 to the negative 5th, because then you will get the wrong answer. We calculate the Grashof number now. We get 2.003 times 10 to the 7th. So let's see what the ratio is. So now the Grashof number to the ratio of Reynolds squared. So Grashof we said was 2.003 times 10 to the 7. 4975 squared. We get 0.809. So we look at our rules over here. If it's about 0.1 or less, then it's forced. If it's about 10, then natural convection. We get 0.8. That's about 1. So neither of those we can assume. So that means both forced and natural convection. So that means we have to solve these separately. So we're going to first calculate the Nusselt number of natural convection. For a flat plate, that is about 0.59 times the Rayleigh number to the 1/4. And so the Rayleigh number, we haven't calculated that. That's just the Grashof number times the Prandtl number. We have the Prandtl number right here, 0.7282. I don't know why there's a dash there. But we have the Grashof number, so we can calculate that. 0.59 times 2.003 times 10 to the 7. That's the Grashof number. Times the Prandtl number, 0.7282. And all of this is to the 1/4. Be sure to have your parentheses right here, because again, if you mess up them, then you will get the wrong answer. Be very careful with how you set up your parentheses. But you get a Nusselt number of 36.46. And then Nusselt number for forced convection is what we were doing in chapter 7, I believe. And so we have all of these things. It's for forced convection over a flat plate. So that's what this is for. Four, 9, 7, 5 to the 0.5 times 0.7282 to the 1/3. And we get 42.14. But that's not what the question was asking. We want to figure out the Nusselt number for each case. Assisting flow and opposing flow. Let's start with assisting because it's first. Assisting flow. So the equation is Nusselt to the 3rd for forced it's technically to the n plus or minus Nusselt number. That looks like a W. Nusselt number natural to the n to the 1/n. For most cases, n will be 3. Plus is assisting, minus is opposing. So, for assisting flow, we have Nu forced to the 3rd plus Nu to the 3rd for natural to the 1/3. And then we start plugging in our numbers. We get 42.14 cubed plus 36.46 cubed to the 1/3. And you get 49.8. And opposing flow, still basically the same formula except we subtract. I wrote a plus. So now we're going to subtract. Subtract 36.46 cubed, and then you take the cubed root. That is 29.8. And those are our answers. So, the question doesn't ask, but if you wanted to, you could use this, solve for h in both cases, and then solve for q to compare the rate of heat transfer, which it very well may do. So that is how we do assisting and opposing flows.